Hello everyone, welcome back to MindMatrix YouTube channel. So I'm Sachin, today starting with probabilities next part. So in the last session we have already seen the basics of counting. So I have divided the last part into three sessions. One was involving, so it was entirety of counting topic. So within that we have seen permutation, combination and distribution. Okay, and then later on we have already solved questions which were being asked in GATE exam, including the one we had in 2023 exam. Okay, so today I'll be proceeding further. Within that will be I'll be covering what exactly we are going to have today. Okay, so a brief intro about myself. I'm upcoming data scientist at Low India, pursuing M.Tech AI right now at IISc Bangalore. So if I talk about experience, I already have 3+ years of experience within this GATE industry and mentored more than 1,000 students. And further on, I had all India rank 70 in GATE CS 2020 exam. Okay, so yeah, that's it. In short, you can see rest of them over here. So today the agenda is going to be motivation, basically just to give you an insight that okay, how much probability is important in real life. And then we'll talk about some basic definition. Okay, a basic, not exactly the definition, but what exactly is probability. We'll be talking about that because definition will cover in the next session. So what exactly is probability? We'll talk about that in a basic sense, and then what are the different interpretation of the probability we're having. A basic example which will be telling us what exactly are the different terms which get to, which gets involved when we discuss probability. And then next we will be discussing brief overview of set theory, which is required over here. I'll just brief you around that. I guess you already have the knowledge around the set theory. Okay, so let's move further with the topic. So if I talk about the motivation, so you must be knowing already recommended systems. You use Netflix, Amazon Prime, Spotify. Okay, you have seen opinion polls, sample surveys you have seen. So these are useful because we can, if we have enough of data, we can always predict the behavior of our customers or population if we have enough of data. For an example, if we have seen that, I guess, Social Network is was the documentary on Netflix. I guess it's available. So if we have enough of data about any consumer, any person, we can always predict what's gonna happen or what decision he or she can take. There is a one good example if you have seen Asur web series as well. So Asur web series second season, if you'll just see that, you'll get to know that how good predictive models can lead to something. You can always tell what exactly this person is going to do next if they have enough of data of that particular person. Okay, so yeah, over there it's like probability which is being used at the basics, at the foundation level. We may use probability models for analyzing algorithms. If you have seen, quick sorts, time complexity, when we find out the average case of that, time complexity, we always use some kind of randomization over there. Okay, and whenever we talk about random phenomena or introduce some kind of randomness, it is always that we are introducing probability theory over there or some kind of probabilistic modeling over there. Okay, so similarly we have, you have seen in computer networks as well, we have the Aloha protocol. Okay, so when we have a shared channel, to what transmit our data, then there may be some kind of collisions happening. So over here we have this kind of protocol. I can't recall what exactly was Aloha, but yeah, there is also kind of a randomness which we introduce, that there is a probability of collision or probability of sending some data at same point of time. So we model or we use probability there as well. And risk assessment in gambling, that what are the chances of winning after you have played this much, and what, further. So over there also it's like probability which is being used at the foundation step. So I have a good question over here. This is like quite a famous question. So just for an example, you can think on your own over here, that let's say uh, somebody okay, let's talk about a fair coin only. Okay, so if I talk about fair coin, let's suppose somebody has repeated an experiment uh 9 times. He has tossed a coin. 9 times somebody has, tossed a coin, and there was always tail which was coming up. We know that the coin is fair, and 9 times it was a head. Let's say 9 times. Let me just write it. It's a good example to discuss over here. So let's say we have tossed 9 times, okay, and we had what? We have got 9 heads only, and we know that the coin was fair only. Okay, the coin was fair. We already know that. And if I just, what should I say? Let's make it 8. Okay, 8 times, and I got 8 heads only. Okay. So if I talk about, should it be like this only? Mm, yeah. Okay. Let's talk about 8 only over here. So 8 times I have tossed the coin, and 8 times I have got the head. Okay, and it was a fair coin. So if I just talk about, two more tosses, two more tosses. So what do you think must be the probability of occurring a tail, or in the next one, or in the next two? What is the probability? I'm just asking you for a brief idea, like would it be less than 0.5, more than 0.5? Just that is the only thing I'm asking. Okay, so let's suppose we have to toss a total of 10 times as I asked. Okay, 8 times we have already tossed. 8 times we have already tossed, and the 8 times result was that we had 8 heads, and only two more times are left over here, and we are, tossing the coin again 2 more times. So what is the probability? Should it be less than 0.5, more than 0.5? So the answer is going to be, it is going to be 0.5 if it's like a fair coin. Okay, so most of the student, and it happens in the gambling as well. Okay, so somebody might think that I have lost. Let's consider head to be kind of, a person can either win or lose. This is the kind of stuff. Okay, so let's represent lose with a head. I'm just taking an example. I'm not getting into the depth. Just giving you a small example over here. Okay, and win with the tail. So if I say that somebody who was about to play 10 games, and he had already lost 8 times, then is it so that when he's playing ninth time he has more chance of winning? The answer is no. If even if he, loses 9 times out of 10, even then for the 10th game there is no chances, no better chances that he may win, because the probability will always remain same. His history or past is past. Whenever we are repeating an experiment, it is always a fresh experiment with the same probabilities we started with. Okay, so I hope the example I wanted to convey over here is clear. Just again, I'll just repeat it in short. That in gambling, most of the people just think about that okay, out of 5 times, if I have lost 4 times, so fifth time I have a good chance of winning, because overall the distribution, so overall, some kind of balance must be maintained, as we already know. Just to give you an example, that uh, the sum of probability is always one. So there are, like, the negative thing and positive thing must cancel out. Losing and winning must cancel out. So person might think, if I have lost 4 times, I have better chance of, winning in my last chance, which is like fifth chance. So there won't be like higher chances. It would always be same number of chances which he had on the first chance, second chance, third chance, or fourth chance. The probability doesn't change over there. Okay, I hope the idea is clear. So the kind of risk assessment in gambling over there also, this kind of probability is being used. This was just a basic idea how it can be used. Okay, if I talk about more about it, so understanding probability can help us make decisions, make predictions, make better decisions, assess the risk, calculated risk. If we talk about, even make money, be it in share market, or like kind of any investment market, if we talk about. Okay, like for the retail, so not the retail, I'm talking about real estate. So if you have good knowledge that okay, market is crashing, going up, what are the chances, you can always make more money. And lastly, to deal with uncertainties. Okay, the thing you're not sure about, that this may happen, that may happen. I hope the idea is clear. So here is a kind of map from one of the reference book, which is Mathematics for Machine Learning. So if I talk about these green boxes, these are, so overall these represent some kind of concepts which is being used in this book. And if I talk about all these, so these are somewhat belong to the probability chapter. And over here, these chapter 9, 10, and 11, these represent machine learning chapters. So it is telling us that how these are being used in machine learning chapters. So this is kind of just arrow are representing that. And more about the terms we'll get to know later when we'll study the machine learning. I hope basic point is clear that yeah, probability is important over here. Okay, so just to give you three examples are being used over here: regression, dimensionality reduction, and density estimation. Let's move further. So this is a kind of theoretical lecture of this lecture, because we need to build better basics to understand everything. Again, you can just get this. Okay, what is probability theory? So it is branch of mathematics dealing with modeling and analysis of random phenomena. As I mentioned, whenever there is kind of randomness coming up, so we are talking about some kind of probability theory there. Okay, statistics, if I talk about that, so statistic is all about drawing inferences from the data, and for that we need probability theory. Okay, so I hope the idea is clear. First will be modeling and kind of analyzing the data, and then we'll be making some kind of conclusion, inferences, or we'll be developing some insights. So there the second part deals with the statistics, and modeling and all analysis involves this probability modeling or probability theory. Okay, so over here again, this is from one of the book from University of Toronto, so I have picked this up from there. Complete list of references are being attached in the last slide. So you can see probability is the science of uncertainty. It provides precise mathematical rules for understanding and analyzing our own ignorance. Because many a times we think that, okay, this is deterministic, this is going to happen, I'm sure about that. But is it true that it is 100% sure it is that that thing must be happening? There may be some kind of ignorance, basically possibilities of something else happening which can be there. Okay, it doesn't tell us tomorrow's weather, हमें नहीं बताता. It doesn't tell what exactly is going to be the weather, stock prices, but it gives us framework to deal with these kind of things with limited knowledge of what we are having to make better decisions. Okay, of what we know or what we do not know. Okay, so like it was first, the probability theory was first discussed and formulated in 17th century, and it was firstly discussed for gambling to quantify the winning and losing. Okay, so let's talk about the interpretation over here. So there are like three kind of general interpretation, and these are the terms which are being mostly used when we talk in machine learning. Okay, so classical interpretation of probability tells that there are equal chances of every occurrence possible. Okay, so it tells about equiprobability stuff. Okay, so and that's what we study when we are like very young ones. When the probability chapter comes for the first time, we study this thing only, that okay, that for an example, there is always this thing mentioned whenever we study that there is well-shuffled deck of cards, there is an unbiased coin, there is a fair dice. So by adding these kind of what should I say, prefixes, not prefixes, but kind of some words using before this. So what does this determine? That we are making sure that every outcome must have equal chances, equal probabilities. That's what our classical approach is. So maybe like for the first time when a student is studying probability, if you ask that person, okay, if you ask that student what are the chances of raining, so he might say that okay, it's 0.5, because either it will rain or it will not, and he has thought only two possibilities are there. So that is the classical approach, giving equal chance to each of the outcome. Okay, now what about the frequentist? So if I talk about frequentist, that is basically related to frequency. So when we talk about frequency, with the frequency for determining probability. That is a frequentist approach. For an example, it deals with a kind of stuff that we are repeating an experiment quite enough number of times to draw conclusion that okay, this is the number of chances of occurring this thing. There is a relative chance with respect to complete scenario. For an example, if you might be not telling that okay, only on one toss or two toss, you're not going to tell that okay, the probability of getting a head or a tail is 0.5. You would be repeating that 1,000 times, maybe 100 times, maybe million times. That is a kind of your recording the frequency for each one of these. For an example, for head, you might be getting some kind of if you have tossed it for 100 times, you may say okay, it is coming out to be approximately 0.5 because you got 49 times head, 51 times tail, something like that. So you are talking about frequency over there, relative frequency, okay, with respect to the total experiments being conducted. But there is a drawback with respect to this, as with classical approach was, because there are not equal probable chances for everything. For classical, I'm talking. And if I talk about the frequency, there are some experiments which cannot be repeated enough number of times. For an example, if I talk about somebody getting married, what are the chances of somebody getting married? So we can't repeat that experiment enough number of times. Okay. Uh, for example, what are the chances of getting some kind of output from this kind of research being uh, which is going on? So what are the chances? That is only when that is we cannot repeat the number of experiments there to say that what are the chances of happening. And we always talk about large enough number of times. We are not talking about okay, 2 3 times, 5 times, 10 times. We don't talk about that. Okay. So always relative frequency. By relative frequency, we tells okay, the probability. What exactly is the probability? Which is not a good estimate, because even if we repeat, for an example, for chances of head, even if we repeat, uh, you know 10 lakh, that is 1 million times of tosses are there, can we say that we will be having exact 5 lakh of heads and 5 lakh, basically point 0.5 million of heads would be there and point 0.5 millions of tail would be there? No, it won't be like that. There would be some plus minuses, and it won't be like exactly +2 +5. There may be bigger gaps as well, which is possible. So this is kind of frequentist approach when we talk about the frequency, relative frequency. What is the Bayesian or subjective approach? It always talks about having some prior knowledge for determining the probability. For an example, if you want to say that okay, somebody getting married, let's suppose, for an example. So if I'm a guy, okay, if I know, let me be the one who is telling the probability of one of my friend getting married. So if I know his status, okay, that he had worked enough in the job, he has earned good amount, he is looking for settling up, and he has a girlfriend, and the parents are also aware about her, then there is a good probability. I know I can say it's 0.99 or 0.999 or 0.95, something like that. I can always say the probability. And if I am the one who doesn't know, okay, that how long he has been working, has he entered just now, because somebody just entered into the industry may not be getting married very soon. Okay, I don't have any idea about that. And even I don't know whether he has a girlfriend or in a relationship or like that. I don't have any idea. So I might say it's like 0.5 as like classical approach. Or I may be thinking that okay, like based on my idea that okay, within his family people haven't married very soon, so the probability is very less. So I may say 0.1. So it is always subjective with respect to your prior knowledge. That is the Bayesian approach of probability. Basically, using the prior knowledge for determining the chances of some occurrence. That is the Bayesian interpretation or subjective interpretation. I hope all these interpretations are clear. So over here we'll discuss what exactly is the idea of probability with the help of an example, and we'll discuss some of the definition which are involved, which we will be discussing in the next session. Okay, but just to have an overview over here, we'll be discussing that. So let's say the question is okay. The question is you need to find out the probability of getting a number larger than 4, which is odd, number, which is odd. Okay, we need to find this probability. So like, basic mathematical calculation I'm asking you for. So what you can do, like, you already know, you can always tell, like, okay, let me just write first of all, let me write the outputs which are overall possible. So let's say you are talking about, larger than 4, so there are two numbers only. And if I talk about the odd numbers, so there are 1, 3 and 5. These are the three numbers which are odd, and these are the two numbers which are greater than 4. So what is the probability? There is only one number satisfying both the conditions, so you'll say it's 1 by 6. As simple as that. But now the question arises, what was the 6? What was this 1? And what exactly is this 1 by 6? What is this telling me? So we have to get to those kind of basics to understand everything over here. Okay, so let me just tell you. So 6 over here represents size of my sample space. We'll discuss what exactly is sample space, but just to understand, okay, in brief right now, I'll just tell you sample space is, total possible outcomes. Okay, what are the total possible outcomes? That represents my sample space, and size of sample space is 6, because there are only six outcomes which are possible. Okay, now the tossing, basically, throwing a die was an experiment which was being conducted. What was it? When we threw a dice, it was an experiment which was being conducted. That also depends how many times we are conducting this experiment. Okay, it was an experiment. And if I talk about number larger than 4, odd, then I'm talking about events. What I'm talking about? I'm talking about some events taking place. Okay, so events would be something which would be there from our sample space. Events would be something from our sample space. Okay, so events also represent some kind of subset of what? Sample space. We'll discuss about all these things in detail in the next session. So over here, 1 is representing the size of my event. Okay, so what was my event? If I talk about the first one, this E1, this was like, what are the number of numbers possible which are larger than 4? So I have 2. So I had this thing, events and sample space, all these represent some kind of set. So that's why I have mentioned that we'll be discussing some part of set also. So 5 and 6. If I talk about odd numbers, that is another event. Let's say, so that is 1, 3, 5. And the event we are talking about is going to be intersection of E1 and E2, the common one, which is 5 only. So what is the size of this? Size of this is 1. We have only one number satisfying this condition. So now what I'm doing is 1 by 6 I'm doing. 1 by 6 I'm doing. 1 by 6. Now it tells me relative size of my event. What is it telling me? It is telling me relative size of my event. Relative size of my event. Okay, with respect to my sample space. So probability is giving me a kind of relative measure of the size of my event. What did I mention? It is giving me a relative measure of my event size with respect to what? When I talk about the word relative, that is always with respect to something, and that is with respect to my sample space. So probability is a kind of measure of what? Size of the set. That what was the relative size of my event with respect to the sample space. Okay, so I hope this part, whatever is being told over here, that is clear. So probability is a kind of measurement. Okay, it is a kind of measurement, but is it actually a measurement? We'll discuss about that later. Okay, that makes part the completely, different topic emerges from that, which is like measure theory. Okay, we'll discuss something like that in brief later on. But right now, just remember, probability is a kind of measure we have, and that is always a size of a set with respect to our sample space. And what was the set I was talking about? The event that represent the set. Okay, so basic terminology is, what was this ratio, why was this 1, why was this 6? Okay, so 1 was representing size of our event which we were interested into, 6 was the size of my what sample space I had, and the ratio is probability, which is basically telling me the relative size with respect to my sample space. I hope the basic ideas are clear over here. So as I mentioned, so I'll be discussing in brief about, these topics over here, the overview of set theory, because they may be required when we study further. Okay, when we proceed further. So what are open and closed interval? So I'll just give you an example. If I have written 3 comma 4 like this, if I have written 3 comma 4 like this, if I have written like this, you might have studied this in your lower classes when you were in school. So what does these things represent? So this interval tells me what is being included in my set. What is being included in my set. So we might represent a range. We might represent a range of numbers with the help of interval. So in all of these, we are talking about 3 to 4. Whatever numbers are there, we are talking about 3 to 4. But whether 3 and 4 are included or not are represented using these braces we have used, the kind of bracket we have used, whether it is a square bracket or it's like this, a normal bracket, parenthesis we are using. So if I talk about this one, so if you remember this, let me just draw this. So if I have something like this, so it's 1, 2, 3 and 4. Okay, I'll just give you this one's example. So over here we represent it by this one on the number line. Let me just use some other color. So we represent this interval, the numbers included in this interval or in this range will be represented by this. It means 3 and 4 are not included, and whatever numbers lies in between them are the part of this range, So you can always say 3.00000, that will be part of this interval. Okay, but not 3. Exactly 3 won't be part of this interval. 3.000, 100 times 0, 1000 times, lakh times 0, and then 1, 2, 3 something will be part of this interval, but not exactly 3. Similarly for 4, when we are talking about 3 to 4, so 4 will never be part of it, but any number less than 4 will always be part of, any number less than 4 greater than 3 will always be part of this interval. So it can be like 3.999999999 up to whatever number of times you want to talk. Okay, then that number belongs to this range, but you can never say that 4 belongs to this interval. Okay, and that is represented by this. And if I talk about this line, so let me just draw all these lines first. So okay, 3 and 4, 3 and 4, and let's say 3 and 4. Okay, how do we represent all these intervals? I've just taken some example over here. So if I talk about the second one, it tells that 3. So over here we have taken, it was not completely filled circles. We have represented by empty circles on the exact number. But over here we are using filled circle, which means These numbers are also part of the intervals. These numbers are also part of the intervals. That means all the numbers starting from 3, including 3, till 4th being included is part of this interval. Okay, that is the part of this range. If I talk about this, so again, this is open. Okay, open. The square bracket represents closed and this represents open. So if I talk about this, so over here now it is like this. So 3 is not part of this, but 4 is. So every number except 3, which is greater than 3, so 3.000 will belong to this, but not 3. But number, because see, this is a square bracket, so 4 will be part of this interval for sure. And similarly, if I talk about this, so 3 will be part of this, but not 4. So I'll just keep this open. Okay, this is not completely filled. I hope the idea is clear. And always remember, whenever we use infinity in any of the end, because entire real number can be represented by this minus infinity to infinity. Always remember, for infinity we always use open interval because we are not sure what exactly infinity represents. So we cannot say that infinity is included, because for every number you say there is always a greater number than that which is part of infinity. Okay, so we never use this kind of thing or this kind of thing whenever we are having infinity, okay, at any end. I hope that is clear. So infinity are being used with open braces only, and then I guess all of these are clear, that what is included, what is not. Further, if I talk about operations, so like union, intersection, subset, power set, okay, whatnot, and then there is a difference, there is a complement. I hope you already know that. So like, in short, what exactly is different? So in the next slide I have the complete what should I say, a table for representing all the operation, which you can refer, being taken from Kenneth Rosen book. So a minus b, let's see, what does this represent? So I'm just telling you in brief only. So a minus b simply means element belonging to A but not C. Belonging to A but not C. Belonging to A but not B, sorry, but not B. A minus B represents that set which says basically whatever set will be formed by this one will be consisting of elements from only A, which are not part of B, which are not part of B. A के एलिमेंट होने चाहिए, B के पार्ट नहीं होने चाहिए, ठीक है? That will be that will be represented by A minus B, like very small stuff. Okay, we'll discuss whenever the examples would be coming up. Okay, this can also be written like A intersection B complement. You must be knowing what exactly is a complement. Okay, so these you must have studied. Universal set, empty set, you must be knowing about these kind of thing. Okay, so that's like a small brief overview you must be having. I'm just want to recall what exactly are these operations, because this can be required. These are the most important thing I wanted to discuss. Okay. So infinite union is basically when you are having sets with finite elements, but you are having infinite such sets. So when you take a union of them, what is happening in that case? I have a simple example to discuss about it. And then similarly for the intersection, okay, we have the example, we'll discuss that. Okay, and that will be involving this kind of open and closed interval. Now if I talk about the disjoint set, that simply means that their intersection is phi, that is empty set, there is nothing is common in between them. Okay, and if I talk about the partition, this is really important. Okay, this is really important. So where should I write? Okay, let me just write it over here only. So partition, if I say that A1, A2 up to AN are partition of A, if I say are partition of A, A, then it always means that there is nothing common in between any of these. First point, they are disjoint. To be a partition, they are disjoint. That means if you take intersection of a1 a2 or a2 a5 or an a3, whatever, pick any one, those will always be disjoint. Basically nothing would be common in between them. The second must be, they must decompose a. That means basically what I'm telling you is, if you take a union of all, I starting from 1 to n, this is representing union of ai. What is this? A1 union a2 union up to an must be a. That means, what is a partition? If I have some number of subsets or some number of sets, I'll say these are partition of this set, because for something it is a partition. I'll say these sets are partition of this set only if they are disjoint. Basically, nothing is common in between them, and if we combine all of them, we'll create the main set we are talking about. Then it's a partition, and that's what we should be like knowing. Okay, that is like by default. It's with quite usual general stuff, not something different. But these property you should be remembering. And similarly, one thing, I'll just remove these. Okay, and at last point, if this is we'll be using this, that let's suppose again same thing, a1 a2 a3 up to an are partition of a, and b is a subset of a. B is a subset of a. That means b has been made by deriving some elements from a. Now it may be having all the elements or no element, but it has been made by deriving some elements of a. So now you can create a partition of b by using a1 a2 a3 an. How? You'll write b intersection a1, b intersection a2, and so on up to b intersection an. These will create partition. So let's say this is b dash 1, this is b dash 2, this is b dash n. Now b1 dash, b2 dash, bn dash, or whatever, from b1 dash to bn dash, these are partition of b now. These are partition of b now. Why? Because see, these were already partition of a, and we have already said that b has been taken from a. So if I talk about, if these were disjoint, then for sure all of these would be disjoint. All of these would be disjoint. And if you just use a law, that means b intersection a1 and then take a union b intersection a2, you'll realize what you'll be coming up with. It would be something like b intersection a1 union a2 union up to an, which is what? This is a, and b intersection a is b only, because b was a subset of a. So that means these will form a partition of b. I hope this is clear. A brief idea that how we can create partition of a subset if we have a partition of already existing bigger set. Okay, I hope this is clear. When a1 a2 a3 were the partitions of a, then how we can create a partition of b, which is a subset of a. I hope this is clear. So let's move on to the next one. So these are the identities I was talking about, taken from Kenneth Rosen. So you must be knowing these simple identities we are having. So yeah, now I'll talk about the infinite union and infinite intersection. And this is going to be the last one, and then we'll solve a question, I guess, simple question, and then we'll end this session. So yeah, let's solve. So this is infinite intersection. You just tell me this. If you put, so n value will start from 1 to infinity. N value will start from, n is from 1 to infinity. Okay, so let's see what are the intervals we are getting, and then we will talk about their intersection. So the first one, if I put n equals 1, what is that? A comma b plus 1, and this is closed and this is open. This was open. For this one we are just discussing it. Okay, so this was n equals 1. When n equals 10, because we'll keep on increasing, so it is a comma b plus 10. If n is 100, what is it then? It is a comma b plus 100, and something like this. So if I keep on increasing, you just tell me, and if I take the intersection of all these, what I'll be coming up with? What I'll be coming up with? So it is for sure that, okay, when I'll be taking the, so and can be like, I'm starting over here from 1, I'm starting it from 1. Okay, but it can, yeah, sorry, yeah, 1 only, 1, or it can be, yeah, it is going to be 1 only. So if I talk about this thing, what I'll be getting an answer, what would be my answer over here? So you can see over here, sorry, one thing I have missed out. This is 1 by 10, 1 by 100. Yeah, so if I just draw a number line, then you'll realize that, okay, A was already included, A, and if I say this was B, then this was B plus 1. Let's suppose this was B plus 1. So when I'm doing B plus 10, I'm coming this side, because 1 is greater than 1 by 10. 1 by 10 is greater than 1 by 100. So you must be knowing, as I'm increasing n, I'm moving towards left. As I'm increasing n, I'm moving towards left. For the first value, it was b plus 1. For the second value, it is b plus 0.1. For the third value, basically, not the third exactly, but the values I have considered, for n equals 100, it is b plus 0.001. So you can see this. Earlier, it was b plus 1. Then from b plus 1, so basically, as I'm increasing the value of n, I'm moving towards the b. So that means if I talk about, if n is, let's suppose, a large number, 10 to the power 10. So in that case, b plus, it would be 0.0000000, and then something like this. So that means it is moving towards left. And if I take the intersection of all of these, so what is going to be the intersection? What would be the common elements? A would be definitely part of it, because it was already included in each of these set. All the numbers in between would be part of that. B will always be part of that, because see, in fact, even if I talk about n equals infinity, it would be something like b plus 0.00000 infinite 0, and then something like 1 or 2 can be there. So that means b is already part of that. But can I say some number greater than b can be there? No, that won't be happening if I take the intersection. Okay, because for every number, let's suppose you say that a plus b, sorry, b plus 0 point, let's suppose 100 times 0 you put, and then you put 1, then you'll say that, okay, this will be included. But it is not the case, because there is another interval which will not be less than this, which will be considering a number less than this. If I just take, if you have put n equals 100 over there, I can say n equals 1000. So in that case, it will be a shorter one, the interval will become shorter one. And if I take the intersection for that, so this number will not be included in that. So that means for the intersection, this is coming towards the left, and I am sure about that b will definitely be part of that interval, because every time b is part of it. But any number greater than that, if I consider, even in the points, there will always be some number which is less than that, which is which is less than that, which when I'll be taking the intersection, the bigger one would be cancelled out, because they are not common in that case. So till b, it is definitely always going to be the common one. If I say anything beyond that, that will never be part of it. So the answer for this one is a comma b. It would be close interval for both. It would be close interval for both. A was already included, we know. Okay, for b, it is going to be close interval. Beyond that, there is nothing which we will be considering, because it was intersection and all the numbers above that were, were not common to all the intervals, because for the intersection the common numbers must only be considered. I hope the idea is clear over here. This was very important. Okay, so let's talk about the next example what we are having, and just erase it. Okay, let's talk about this similarly. So let's put n equals 1, n equals 10, n equals 1000, sorry, 100, 1000, and then you'll get to know what exactly we are coming up with. So this is a comma b minus 1, and both are closed. For this one, it would be a comma b minus 0.1. For this one, it will be a comma b minus 0.01. Okay, and similarly, a comma b minus 0.001. So you can see over here, what are we coming up with over here? So if this is a, which is definitely included, we know. If over here I put b, and if I put, b minus 1 over here, let's suppose b minus 1 is present over here. Okay, so for the first one, we have a to b minus 1, and then I have to take a union with the next number, which would be greater than that, obviously, because if I keep decreasing on the number which is which is being subtracted from my main number, it will be increasing. For an example, just to give you an idea, so 5 minus 1 is 4, but 5 minus 0.1 is 4.9. 5 minus 0.01 is 4.99. So you can see over here, yeah, how it is coming up. Okay, earlier it was 4 only, then it is becoming 4.9, then it is becoming 4.99, and similarly we keep on going towards the number further. Okay, we will keep on going towards the b. When we had like b minus 1, which was 4, and then like if I take b equals 5, then you can see this was 4, then I got 4.9, then I got 4.99, then I further got 4.999, and similarly we keep on going. But will I be able to reach a point which is like 5 itself? Will I be ever able to reach a point of 5 always? I will be definitely reaching 4.9999, maybe infinite times of 9, because n is going till infinite. So maybe it's like 9 can be repeated infinite times. But will I be ever reaching 5? Because to reach 5, this number must be 0. But if I say n is a integer, and we are going till last, so this will never be 0. This will be close to 0, but never 0. So we will never be reaching a point of 5. We will never be reaching a point of 5. That means b will never become part of b. But any number less than b will always be part of what? My set. Any number less than b will always be part of my set. I can never say that for some value of n, I will get this as b. This will be returning me b, because n will be some large number, so this is coming out to be 0. This will never be happening. So that means I will never be able to reach 5. But can I reach any number less than 5? The answer is yes. Because if I put n equals, maybe millions and trillions and billions, whatever, I'll be getting a number just less than 5 for sure. That means if I take union of all of these, so this union with another some bigger number, then some more bigger interval, then some more, so union would be coming out to be a would be definitely part of that, and then it will go up to b, but b not included, so open interval, sorry, open braces over here. So I hope the idea is clear. So for this one, we had a comma b like this, and for this one we are having open one, and over here closed. And see the kind of stuff we started with. Over we had this open braces, but we ended up with closed braces. Over here we had closed braces, but we ended up with open braces. The reason, you must be clear right now. Just think about this, how we have solved this. Just think about how we have come up over here by putting different value of n. You'll get to know that, okay, what are the common interval which will be part of this entire set when we take infinite intersection and infinite union. I hope the idea is clear. Okay, and at last, one basic question we'll be solving over here. Okay, so yeah, let's see over here. If a fair coin is tossed n times, what is the probability that the difference between number of heads and tails is equal to n minus 3? So it's very simple problem. Let's see. So, like if I have tossed, let's suppose the head is, the number of head I'm talking about is x. And as I have tossed it, how many times? N times. So number of tails must be what? Y. Number of tails must be y. So that means, it must be n minus x. N minus x. And it is being told the difference must be n minus 3. What is the probability the difference is n minus 3? What is the probability the difference is n minus 3? So if I take a difference, let's suppose that x is greater than n minus x. Let's suppose this is the case. Or you can consider n minus x also to be greater than x. You can consider that as well. Okay, just to give you a context, if n equals 12, I'm discussing the point that whether x, which can be like, okay, x may be 2, or if x is 8. So these are the different scenario. If x equals 8, then n minus x will be less than this, because that would be 4 less than 8. And if x is 2, then n minus x is going to be greater than x, which is going to be 10 greater than 2. I hope the idea is clear what I'm telling. So overall, they are discussing about the difference must be equal to n minus 3. So let's take any of the case and we'll get the answer. So if this is the case, x is greater than n minus x, then in that case, so what is going to be the difference? X minus n minus x, which is going to be 2x minus n. Point is very important. So even if x is greater than this thing, so this must be a kind of value we must be getting for the difference. But the difference over here is something like n minus 3. So okay, we may consider that n is common into that. That means 2x must be somewhere, it must correspond to 3. That means, like, if I talk about what would be the values I'll be getting, so it would be something like, okay, the difference can be either n minus 2, or difference can be n minus 4, n minus 6, n minus 8, and something like this. It will never be the case that I'll be getting n minus 3. It will never be the case that I'll be getting n minus 3 for sure. Okay, so these are the kind of values I'll be getting, even if I consider that x is greater than n minus 6. For this, I'll get this equation, and if I consider this, I'll be getting something like, okay, n minus x, which is like n minus 2x. So from this also, because this is the case, so you can start putting value from x equals 1. So that's what you'll be getting over here. And if this is the case, you'll be starting something from greater than n by 2. So even then you'll be getting something like this, the integer value greater than n by 2. Okay, so you can see every time we'll be getting some kind of, the difference would be something like n minus 2, n minus 4, n minus 6, n minus 8. So basically something even number is getting subtracted from n, not an odd number. So this is not possible. So the probability is 0. So the answer is 0. I hope it is clear. Okay, so now this was all the basic stuff we need to discuss. In further session, we'll be talking about the axioms and the laws. Okay, and these are the basic references I have used over here. Okay, and you can join our Telegram group, or you can follow us on Instagram, and this is the link for our WhatsApp channel. Okay, to stay connected. Thank you guys. Bye bye. Take care.